Now, naturally, since we're using vectors instead of functions, you're probably more familiar with eigenvectors instead of eigenfunctions, and that means instead of an operator solving things, it's going to be a matrix solving the equation. So where does the matrix come from? Well, actually, that's relatively easy to work with. Since we're doing a 2x2 matrix, that makes things even easier to work with by brute force. I don't even have to put effort into actually solving the eigenvalue equation, which means that we can take SZF is equal to MH bar F, and then say, well, F is going to be equal to LM. Then what is SZ? Well, let's say it's a matrix A, B, C, D. I don't know. Who knows? And that matrix is going to give us A, B, C, D times LM is equal to MH bar LM. And in our case, the LM in question is half-half, and we get returned half H bar half-half. Now, there's the other side, which is what happens when we take half minus a half. And we'll look into that very, very soon. So what do we get on this side? Well, we get half A plus half B, half C plus half D. No big deal. Is equal to half H bar half half. Now, when you multiply both sides by 2, you get A plus B is equal to H bar over 2, and C plus D is equal to H bar over 2. Great, we have 4 unknowns and 2 equations. That's not going to work. So, we have to take into account the other possible spin state. Spin down. Once we do that, we get a set of totally different equations. Not totally different. We get this is equal to minus this minus this. And what does that tell us? Well, that tells us that half, or A minus B, is equal to minus H bar over 2. And it also tells us that C minus D is equal to H bar over 2. Hey, wait a minute. That means B is just H bar over 2. C is minus H bar over 2. Wait, no. Sorry. B is minus H bar over 2. C is H bar over 2. And the other 2 components are 0. Which means that the LZ matrix has to be what? H bar over 2 multiplied by 0.